Okay, boys, so I did not solve day 20 yet. Instead, I skipped straight to day 21 because it looked much more simpler. I still don't understand something about day 20, so when the broadcaster sent it to this, everything happens simultaneously. So, if you send it to A, right? A sends to B. So at the same time, A and B already received a low input. I don't freaking know. Bro, I don't know. But anyways, I thought since day 21 is much easier to understand for me, I might as well solve it first, and I did. It's actually very simple, so I think I just have to, I already put it in. 65, 3605. Perfect cubes. Okay. Wait, what is... Okay, so the map repeats. So how do I... It's a tiny 3 map. So it's all... So there's one S. I still don't get what the perfect cubes or squares have to do with this. I don't get it. So let me analyze the input. So it's surrounded by the dot. So that's one thing guaranteed. So I'm gonna have to think a little bit about this. So we definitely need to be able to... Okay, so if you have like... Yeah, give me a second to think about this. Hi guys, welcome to another video. Now this is, again, super duper late, but I finally solved day 21, both parts. So I don't know why day 21 is actually quite tricky, and the overall experience is just quite hard. So let's go over day 21. So for part 1, you're given a grid, you start at wherever S is, and you figure out how many things you can reach within steps, right? But like the thing is, you have to worry about the parity. So if, for example, the number of steps is even number, then you have to look for the number of places you can reach that has the same parity. Right? Because every single time you move one step, you change the parity of your coordinate. So if you move even number of times, then the odd parities, they cancel out, right? So that's part one. You just naively do this. In the grid, if you take a look at it, the actual grid, it's not that big. It's not that big. So part two is where it gets insane. So the grid can repeat in both horizontally and vertically, or diagonally. Can see this is the same grid as the input, but just basically pasted 8 more times. And you have to find out how many spots. You have to be exact. How many spots can you reach? 26 million steps. Now, there's no hacking way you're running 26 million steps natively. And you're not gonna copy paste this entire grid on your own because the grid size is 131 times 131. So that's already 17,000 spots. Imagine creating a grid big enough for 2 million. Like, how do you even do that? So, I'm gonna need paint for this. So, I'm gonna show you how I solved part 2. It's easily hardest part for me by far in this entire year. I've yet to look at part, well, day 20, 22, 23, 24. This is the 24th. So, the idea is instead of like starting from where you start and try to explore the whole thing, you say, okay, if I want to look at this point, right? How many different copies of this point can I get to? So this is this is your starting grid, right? I'll put in the center. And these are your copies. So you go here, right? You go here, there's a copy there, there's a copy here, there's a copy here. So I'm just putting the original grid in the center for easier illustration. So let's say if this is S, right? And you're looking at this point, right? I don't know, maybe I draw some freaking obstacles. So you want to find out how many copies of S you can get to. Then you just apply this for every single point that you can reach, right? Well, we know that the copy of S can be here, here, like I'm just trying my best to illustrate. So you have this point in all the copies. Now, the problem is the shortest path might differ between these. So maybe, for example, this S, you just go straight up. I'll use a different color. You just go straight up and you get S. But for this one, you have to go this way to get S. And this one, you go this way to get S, right? It seems like the problem is so freaking difficult. Like, these are not even the same length. They don't look like the same length. Like, this one's just so short compared to these other three. And you get the idea. So, what do we do? Well, let me take a 1 point for example. So I'm gonna do this. This is just for debugging. So if I go to like 1 and 1, I think this will work. And now we'll use the example grid too. So here we go. I don't even know if it's a same parity. Oh, I should probably increase the number of steps to like so how many steps is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 steps. So basically, this nested for loop is each individual point. So you can see I reach exactly one copy in the top left corner. 0.00. So it turns out if you analyze the sequence, right? So let me print. It's called D. So basically what I've done is I've broken this down into basically 8 cases. So you go straight horizontal. Well, in other words, so you go straight right, straight left, straight down, straight up, and every single point in the top left, or like this quadrant, this quadrant, this quadrant, and this quadrant. So in case it sounds like a lot, but they're so similar. It's just few little things you change, and then they follow pretty common logic. So when you analyze a sequence, so okay, this is a 10 by 10. So I call this a 3 by 3 grid because it's like 3 copies of it by 3 copies of this. So I did 10 by 10. And remember, I'm just looking at the top left point, right? So these are basically, each of these belong to top down left to right directly. And I look at the sequence of shortest paths between each copies of it. So for example, if I'm at, so let's say, if I wanted to look at how many copies of to the right can I make, I look at distance to this and distance to this and many more copies, so up to 10 copies. 1, 2, 3, 4, 5, 6, 7. So it's actually 9 values because one of it would just be the same original grid, which basically pointless to look at. But when you see it, when you go far enough, they start to look like they differ by a constant amount, which is 11. So they differ by 11 because this example grid, right, is 11 by 11. So it differs by the size of the grid. Well, you can take any dimension, width or height. They're the same. The grid is a square. So how can you verify? Well, let's print out the JSON differences. And this is something interesting. So do it's not second minus it's first. So I'm getting all the JSON differences and using the example grid. Good. So you see they differ by 11, 11, 11, 11. But the thing is, these are not always, this is not always the case. So if I go back to analyzing the entire thing, and let's print it out. Let's print out the JSON differences. So you see, here, the first difference is 17, and then you get like 13 here, 15 here, and you see, like, even in this case, the first two elements, the first two differences are not even the same. But you see that it follows a constant pattern after some point. And that is what I found out. So we can conclude that for anything after, so let me just do this. I think this makes it a little bit easier. So let me print this difference thing and print it alongside this. Yeah, so you can see let's say after this difference, right? We can just continue build the sequence by adding multiples of 11. But of course, there's some exceptions where, first like 2 or 3, I don't know how many, doesn't follow the pattern. Then we just check the distances manually. But see, that's the thing. We only need to know up to like, I don't know, 3 copies basically. 3, 4, 5. Just compute the information for those and you're good to go. So what do you do now? Now we find out, okay, how many multiples of the steps we can add such that, so basically, to build a sequence, we take this value, which is the last thing. So d dot last, I'll put it for simplicity, plus k times n is less than steps. Right? This is steps you want to solve. This is the equation we're trying to satisfy. We want to find out what k is. So we do a little bit of algebra, and turns out k is less than steps minus d dot last divided by n. So we find this k. Now what happens when the amount of steps doesn't even go up to 108, for example? Well, k would be 0. So that's fine. Now, there's something I'm not going to explain. I think you could figure out on your own is handling the parity. Because, like, how do I even do this? So, if your steps is like 108, right? So let's say this last is equal to 108, and your steps equals to like 31. So, well, I guess I'll explain a little bit. And then, the, like, I don't know, the n is equal to 11, right? Notice that this last step, it isn't in the same parity. So we're looking only for values that are specific parity in k. So there are k divided by 4, k divided by 2 even numbers, and then there is floor of k plus 1 divided by 2 odd numbers. So remember, even numbers, they keep parity the same. Odd numbers, they flip the parity. So in this case, we started with even number, and we need to get to odd parity because steps itself is odd. So we need, so let's say, like, I don't know, if k is equal to 5, right? Then we know that even is equal to 2, 4, odd 1, 3, 5. We just care about the number of even odd elements. Then we know we obviously need k plus 1 divided by 2. So you solve for the maximum value of k, and then you figure out the parity of numbers you want, and then figure out how many of them exist. So this is the thing I apply. Because yeah, if you think about it, like 108 plus 11 plus 11, 11 plus 11, 22, which is even. So 108 plus 22 is even. So even is not equal odd. So we just handle parity everywhere, but this is essentially what I do. Now I do this for the directions up, down, left, and right. I call this F. I did not care about the naming. I just wanted to solve this. This took me forever. But oh, yeah. Now this function g, what is it doing? It's for the quadrants now. So we're working with quadrants. Now how do I even explain this? So I guess I'll draw a new grid. So this is our frick. This is our starting grid again. I'm gonna work with the top left corner. So top left, right? And then we have something like this, right? Well, I'll give the copies a different color. Say this is our S, right? This is a point we want to look at. So it exists in all copies. Now, what's the minimum amount of moves to get from S to this copy? Well, let's think about it a little bit. So it has to follow certain strategy. If we look at our grid and the example grid, you can see that it's padded with empty spaces, right? So that means you have no obstacles as long as you run along the edge of the grid. Now, why is this important? Well, I'll explain in a little bit. But let me show you something about Manhattan distance. We're basically looking for a Manhattan distance, right? So if you go like this way, so 1, 2, 3, 4, right? This is a Manhattan distance of 4. It's just dx plus dy. So this is how you calculate Manhattan distance. So this is the same as going, so this, down, this, and down. Both taken the 4 steps. This just took a different path. As long as the changing x and y are the same, then you're good. So why don't we go from S to top left corner? Well, I'll give it a different color. So S to top left corner, and then top left corner to here, and top left corner to here. So, well, maybe that's a bad copy. So let's say I want to go here. Let me draw this. This is best example. So we go from S to top left. Then we go here. So this is N, right? And then we go up here, N. And then from here, we go to here. So yeah, this is distance from start to top left plus distance from bottom right to point plus 2. Well, it's plus n plus n plus 2. This 2 is for crossing the edges. But you can see we're traveling by multiples of n. So this is something very important. This is why it's important that the grid is m by n, not like m minus or m times m. What am I saying? It's a square. And we can see that it's optimal to, for this case, to go from start to top left and not any other point. Because, like, if you go like for example, if there's like bunch of obstacles here, right? So let's say there's, I don't know, freaking this, or something, and then something like this. Or maybe this will illustrate the point better. So we have a wall. So at the start, we're forced to go down here, right? But we still have to move up. It doesn't matter when we move up. We can go here, right? And then we move up this way. But we can just move up earlier. So our calculations stay consistent. So this is one great thing about Manhattan distance. As long as your end result is the same, you can change the order which you move. And again, when you have this, right? You have to worry about parity again, because if n is odd, well, you add odd, it add odd. So you end up with even parity, which means the number of moves you done, well, the parity of it is like, it's dependent on this and this. So this is, I don't know, I'll call this A and B. So I have to worry about the parity of A and B, so this, and then I have to worry about parity of like the n. So now equation becomes Kn. I'm just write it down. So now we're solving for K again. How many multiples of n can we make? That this is quite similar to, you know, the up, down, left, right case. We solve for K, but we have to count, because um for example, if we can go here, right? If we go here, we've moved 2 to the left, but we can also go up here. We still make 2 moves, but it's a 1 left, 1 up. So if we think about it, the pattern generalizes down to, so I'll give this to illustrate the point. I actually don't need that. So it becomes a checkerboard pattern when you think about parity. Let's say these are good, right? And then we move up. Remember, that means you have 1 less unit of everything. So then you have this. Well, so you have X is here. X is what we can go to. And then here, the pattern continues. So I have to somehow count the number of X's. So like if, let's call this K. If K is odd, then we do K, so we do this. times k divided by 2 plus 1. Okay, I'll explain this formula. So the summation formula is this. So I'm just using this thing. Where is it? So it's, well, I'll just write it down. Sum of first n numbers, first n positive numbers is n times n plus 1 divided by 2. So you can see I'm figuring out the sum of the first k divided by 2 positive numbers. And why is that? Well, you can see we have 3 x's. We know we have 2 x's and 1 x. Right, then if we have 5 x's, instead of have 4 x's up here, 3 x's up here, 2 x's up here, 1 x up here. So I need to count them in one go. So I use the formula. But you may also notice that they appear twice. 2 x's appear twice, 1 x appear twice. So that must mean if we start at 5, right? 4 x's appear twice, 3 x's appear twice, 2 x's appear twice, 1 x appear twice. So basically I want to take this formula and I want to double the amount. I want to double its sum. Because 1 plus 2 plus 3 plus 4, I want to double this, or I would just want to add itself back, which is equal to this. So that means n times n plus 1 divided by 2. I multiply it by 2, so that just gives me n times n plus 1. So that's why the divided by 2 is gone. So this is odd, right? So if k is even, well, okay, maybe I should do it like this. So if k is even, then we do this. So, and then we do if k is odd. Well, you see, this appeared only once. This appeared only once. So this is also add k plus 1 divided by 2. So this is what I apply for each of the quadrants. So yeah, if you can see, I have this thing. I use this to cast the value to long, or just long in Java. Now, what is this? Well, this is this thing I was talking about. So I just made this really simple example of just look at a parity of k. But we also have to look at a parity of a plus b. So if, again, this goes back to the logic of odd numbers and even numbers. So if the distance of this and this is already odd, and we need the overall parity of the copies to be odd, well, we don't have to move. Oh my god, it's so hard to explain. But yeah, essentially I look at a parity. I'll leave the code in the paste bin so you can analyze it yourself and ask me any clarifying questions. But yeah, the overall idea I hope I explained well. Find how many copy of each point we can reach, and we just use some math stuff to compute it. So GG.